In this video, we are going to talk about matrices without really thinking about their applications. We'll talk more about how we use them in a little bit. Already we've talked about using them as a shorter way of writing a matrix equation, of writing the equation, the matrix A times the vector x is equal to the vector b, so that we could find a system of linear equations as a matrix equation. But today we're going to talk about using matrices or doing operations on matrices that will allow us, while we won't talk about the application so much in this video, it will later allow us to use those operations to simplify a lot of those types of problems later on. So, with that being said, typically we use a capital letter to represent a matrix. So if I write the letter like capital A, the matrix A is equal to, maybe I'm going to say the matrix A is equal to 1, 2, 3, 4, 5, 6, like that. Then we would say that this is a 2 by 3 matrix. So the first number is the number of rows. And the second number, 2 by 3, is the number of columns. And for the matrix capital A, we would refer to the individual numbers inside the matrix, the individual entries, as usually lowercase a, ij, with those just put side by side like that. And this would be the entry in the ith row and jth column. So for instance, in this matrix, A, 2, 3 would be the entry in the second row. So we're talking about the second row. And the third column, this would be equal to 6. And so we can refer to the individual entries by their position. And we put the row first and then the column. So now, once we've got this, we can start talking about how do we actually do operations on matrices. So for that, we need to have a couple of matrices. I'm going to define another matrix B, which will have the exact same dimensions, so 2 by 3. And this one, let's say, is 7, 8, 9, and 1, 2, 3. So we would define A plus B is the matrix whose entries are A11 plus B11, A12 plus B12, A13 plus B13, A21 plus B21, A22 plus B22, and A23 plus B23. That's a long way to write out. You just add up the individual entries separately. So the first entry, the 1, 1 entry is 1 plus 7 is 8. The next is 2 plus 8 is 10. The next is 3 plus 9 is 12. In the next row, we get 4 plus 1 is 5. 5 plus 2 is 7. And 6 plus 3 is 9. So that's A plus B. Notice if I tried to take a third matrix, say C, that is maybe 1, 2, 3, 4, 5, 6. This matrix is a 3 by 2 matrix. So if I take A plus C, I would be getting 1, 2, 3, 4, 5, 6, plus 1, 2, 3, 4, 5, 6. And there aren't corresponding rows and columns. So there is no column that corresponds to the third column and no row that corresponds to the third row. So this does not exist. You cannot add together matrices that have different, that don't have compatible dimensions. Sorry, my nose is a little stuffy today, so I apologize for that. But if we have, let's bring back our matrix A. If I multiply a matrix A by a scalar, C, like lowercase c, maybe in this case, let's say, use as our example the number 2. Then C times A, or written another way, 2A, because C is equal to 2, would be the matrix that is formed by taking 2 times every entry. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 4 times 2 is 8, 5 times 2 is 10, and 6 times 2 is 12. And when I do that, I get this matrix that is, we call this a scalar multiplication. We have just scaled every entry by the amount of our constant multiplier. Okay, so with this said, there are a couple of special matrices that I want to talk about. The first one is the matrix I. This stands for the identity matrix, and this is the matrix that is formed by writing down the diagonal ones and off the diagonals zeros. So it's ones on the diagonal and everywhere else is zeros. And the identity matrix, you can say I sub m if you want to say how many rows and columns there are, but we usually just write the letter I and assume that you'll be able to figure out from context how many rows and columns there are. Notice this is an m by m matrix because all of the numbers are on the diagonal. So it has to be a square matrix, which means that it's got the same number of rows and columns, m by m. And so that's the first matrix that we will refer to. The second one is called the zero matrix. And the zero matrix is a matrix where every single entry is 0. This is an m by n matrix, meaning it can be whatever size you need it to be. And so that we usually, once again, are not going to specify the size, but a zero matrix, you'll be able to figure out what size it is from the context where it's used. And how do we mean that? Well, if I said a plus 0, well, since a is 2 by 3, for this to make any sense, my zero matrix would have to be a 2 by 3. So a plus 0, which would be just a because you're adding 0 to every entry. So this is how we use these two matrices, the identity matrix and the zero matrix. And if we're thinking about what role these play, you can think of the zero matrix if you're thinking about comparing matrices to numbers. The zero matrix is kind of like the number 0, And the identity matrix is kind of like the number 1. Okay, so now we have a few facts that we want to talk about with matrices. So we're going to let A, B, and C be M by N matrices. So I don't know what M and N are in this case, but they're all the same size because they all are M by N. And let R and S be scalars. So it is fairly common to use like a lowercase r, a lowercase s, or a lowercase c to be a constant. I would use a c, except for I'm using the c for the matrix, which makes it to where it feels like lowercase c is related to that matrix, but it's not. But the constants aren't related. They're just numbers. So I'm using r and s to just distinguish them from the matrices that we are starting out with. And we are going to make 6 statements about this. First, let's do it with a dot. First, A plus B is equal to B plus A. That is, the order that you do addition with matrices does not matter. The second fact, A plus B plus C is equal to A plus B plus C. So the you can do the first or the second one in addition in either order. It doesn't matter. The third fact is A plus the 0 matrix is equal to A. The fourth fact is R times the matrix A plus B is equal to R times A plus R times B. You can distribute scalar multiplication. Next, R plus S times A is equal to RA plus SA. And finally, R times SA is equal to RS times A. So the order that you do that you multiply the scalars in doesn't matter. So this is, none of these should be too surprising to you, but it is good to know what they are. The next thing I want to talk about is what happens if we're doing multiplication. So we've already talked about, if I have, say, a matrix 1, 2, 3, 4, 5, 6, and I want to multiply it by a vector, I need to have, in the vector I'm picking, it needs to have the number of rows, the number of rows that the matrix had columns. So I could do something like 7, 8, 9. When I do that multiplication, I multiply the first entry by the first entry. And I get 7 times 1. Then I multiply across that row. So I'm going to write it in the opposite order. 1 times 7. I go across the row, 2, and down the column, times 8. Across the row to 3, down the column, times 9. And I add all of those together. And then for the next row, I'm going to get 4 times 7, 5 times 8, plus 6 times 9. I'm just going across the rows of the matrix and down the column vector. And that gives me the number 7 plus 16 plus 27 is 23 plus 27 is 50. And 28 plus 40 is 68, plus 54. 68 plus 54 is 72 plus 50 is 122. Unless I made a mistake in my quick math in my head. But the thing to notice, if I had a 2 by 3 matrix, I can multiply that by a vector. But a vector I could think of as a 3 by 1 vector. Sorry, a 3 by 1 matrix. And if I'm multiplying a 2 by 3 vector, 2 by 3 matrix times a 3 by 1 matrix, to make this work, I have to have the same number of columns in the matrix as I have rows in the vector, and I end up with a matrix that is a 2 by 1, 2 rows, 1 column. And so I could do this, I could represent this same idea with another vector. I don't necessarily have to just do multiplication by a vector. So let's say 1, 1, 2, 2, 2, 3, and I'm going to multiply that by a vector 1, 1, 2, 2, 3, 3. Actually, let's do something a little different than that. Let's do 1, 1, 1 as my second column. This is a 2 by 3 times a 3 by 2. You can think of this as just this second matrix that we're multiplying by. You can think of it as 2 column vectors side by side. And so to do this, carry out this multiplication, we're going to multiply the matrix times the first column vector, which gives me, remember, you go across the matrix down the vector. So we're going to be working with first the top row and the first column to get 1 times 1 is 1, plus 1 times 2 is 2, plus 2 times 3 is 6. And then we go to the second row, and we get 2 times 1 is 2, plus 2 times 2 is 4, plus 3 times 3 is 9. And then we go and we redo it using the second column vector. So I get 1 times 1 is 1, plus 1 times 1 is 1, plus 2 times 1 is 2. And then the second row, I get 2 times 1 is 2, plus 2 times 1 is 2, plus 3 times 1 is 3. And now if I carry out all those additions, I will see that I'm getting a matrix that is 1 plus 2 plus 6 is 9, 1 plus 1 plus 2 is 4, 2 plus 4 plus 9 is 15, and 2 plus 2 plus 4 is 7, which is a 2 by 2 matrix. So my 3's matched, and I end up with a 2 by 2 matrix. We call this process matrix multiplication. So for matrix multiplication, if I want to take A times B, then I need if A is an M by N matrix and B is an N by, let's say, N by S matrix, then A times B is going to be a M by S matrix. And I can only do this multiplication if the number of columns of my first matrix is the same as the number of rows of my second matrix. And that's going to define matrix multiplication. One of the things that is significant about this is we can think of this because we're multiplying by a collection of vectors, we can think of this as combining multiple multiple vector equations together. And so we can represent multiple vector equations by using matrices instead of vectors. What becomes really valuable for us, though, is when A and B are the same size, they become really useful. This becomes really useful for us in a number of ways. So, if you take a matrix A, let's say that it's n by n, and a matrix B that is also n by n. So since the number of columns matches the number of rows, I'm going to end up with an n by n vector when I multiply it together. And I take an n by n matrix when I multiply it together. And I take a vector v that has n rows. Then I could do the matrix A times the matrix B times V. And this would represent taking this V times B and finding a solution, finding out what I get when I do that multiplication. This B times V is a n row vector, because once I multiply that B times V, I get a vector. And then I can multiply A times an n row vector, the n row vector BV, to get another n row vector. What's really useful for us, what's really nice for us, is using the matrix multiplication that we just defined. I can multiply A times B together first, and then multiply by the vector. And so what I can think about is whatever B is doing to that vector, A is then doing something else to it. The vector AB is combining both actions. So we can combine multiple actions of vectors together by using matrix multiplication. So since we talked about how we can deal with addition and scalar multiplication, let's do the same thing for matrix multiplication. And so this works in general if the sizes work out well, but I'm going to specifically talk about square matrices. So this will work in a broader setting because it will work anytime the sizes of the matrices make the multiplication defined. But we're going to assume that our matrices are all the same size and they're all square so that the sizes just work out for us. So let's let A, B, and C be n by n matrices. And let R be a scalar. Then the following are all true. The matrix A times B times C is equal to the matrix A times B times the matrix C. Second, the matrix A times B plus C is equal to the matrix AB plus the matrix AC. 3, the matrix B plus C times A is equal to the matrix BA plus CA. The fourth, the matrix R times AB is equal to RA times B, which is equal to A times RB. And finally, the identity matrix times A is equal to A, which is equal to A times the identity matrix. Now, so far, none of these seem surprising. This is where things become a little bit unfortunate and surprising for most people who are first getting started. What I cannot say, it is not true that AB is equal to BA. The order of operations matters. So I cannot just turn the matrices around. So let's look at an example of that to see why. So let's look at the matrix 1, 2, 2, 3 times the matrix 3, 1, 1, 2. And I have not actually even bothered to check to make sure that this is going to work out for us, but it usually does because it is very rare that you can switch the order. So let's just go ahead and multiply these together. So we go across the row of the rows in the first matrix and down the columns in the second. So 3 times 1 is 3, plus 2 times 1 is 2, so 3 plus 2 is 5. Then 2 times 3 going across the second row and down the first column. 2 times 3 is 6, plus 3 times 1 is 3, so 6 plus 3 is 9. Now we're in the second column of the second matrix in the first row of the first. So 1 times 1 is 1, plus 2 times 2 is 4, 1 plus 4 is 5. And second row, second column, 1 times 2 is 2, plus 3 times 2 is 6, so 2 plus 6 is 8. And I get this matrix. But if I multiply it the other direction, 3, 1, 1, 2 times 1, 2, 2, 3, then what do I get? I get going across the first row and down the first column, 3 times 1 is 3, plus 2 times 1 is 2, 3 plus 2 is 5. Across the second row and down the first column, 1 times 1 is 1, plus 2 times 2 is 4, 1 plus 4 is 5. Across the first row and down the second column, 3 times 2 is 6, plus 3 times 1 is 3, so 9. And 1 times 2 is 2, plus 2 times 3 is 6, so 8. And notice I got different answers. So I can't just turn the matrices around, to turn the matrices backwards. So what we know then is, in general, AB is not necessarily equal to BA. And it's even worse than that. If AB is equal to AC, this does not imply, does not mean that B is equal to C. So you cannot cancel matrices. And if A times B equals 0, that does not mean, this does not mean that either A or B is 0. So the zero product property does not hold for matrices. So this means that matrices in a lot of ways act like coefficients or numbers in an equation, but it doesn't work with changing the order of multiplication. It does not work with canceling matrices, and you cannot use the zero product property. Okay, so one more really big idea that I want to talk about is the idea of the transpose. So let's look at a square matrix. I'm going to just represent these with letters, and then we'll do an example. This matrix, if we call this matrix A is equal to this, then we define A transpose to be the matrix where we switch the rows and the columns. So the first column of A is AC, so the first row of A transpose would be AC. The second column of A is BD, so the second row of A transpose would be BD. So we just are switching rows and columns. Let's look at another example, this one with actual numbers in it. If we look at B being -5, 2, 1, -3, 0, 4, then B transpose, well, B was a 2 by 3 matrix. B transpose is going to be a 3 by 2 matrix. And the first row of B is going to be the first column of B transpose. The second row of B is the second column of B transpose. The third row of B is the third column of B transpose. So we can define this idea with the transpose, and we have some properties of transposes. So let A and B be matrices. And we want these matrices to be defined with consistent sizes so that all the products and multiplications work. You can think of these as n by n if you want to just only think about the square matrices, but it works as long as the additions or multiplications are defined. So let A and B be matrices and R a scalar. Then if I take A transpose and I transpose that, I get back to A. Secondly, if I take A plus B and I transpose it, I get A transpose plus B transpose. Third, if I take R times A and I transpose that, this is equal to R times A transpose. And the fourth one, that might be the most useful one for us, is if I take A times B and I transpose it, that is equal to B transpose times A transpose. So that is everything we are going to do in this first video for this week. So this video is a little bit shorter, but we've talked about a lot of different operations we can do on matrices. And for our next video, we will talk about finding inverse matrices. So in this video, one of the big limitation we had was that you can't switch the order of multiplication, you can't cancel things out, and you can't assume the zero product property. Effectively, what that means is there is no such thing as a division of a matrix, but In the next video, we're going to find something that's almost as good as division of a matrix. So we will see that next time.